Okay, so good evening, everyone. Welcome to the week 9 session of Basics of Semiconductor Microwave Devices. I'm Shazan Bhatt, and I'm a direct PhD student at IIT Bombay. And this course is offered from by NPTEL, and the course instructor is Professor Digby Joynath from IIC Bangalore. Okay, so we'll get started with this session, and what we are going to cover is BJTs mostly, the common emitter, common base configurations, and we will be covering certain physics-based effects, mostly covering the physics aspects, not the circuit part of it. So this is the brief outline what we have covered till now, till week 8, and we are moving into the week 9 today, where we will be discussing briefly about the BJTs, how they are used at high frequencies, what is the gain, the transconductance, the common emitter, common base configurations, something called as Gummel plots, KIRK effects, and then we will briefly look into the HBTs, and then we will move on to solve some of the problems. So, due to some issue with the Google Meet right now, my video is not popping up here. Otherwise, the camera is on. But anyways, we will move forward. Maybe I have tried a couple of times, but let's see whether it will resolve itself or not. So, anyways, we will start because I hope I'm audible clearly. Uh, so, what we will try to cover today, apart from what I have written, the brief outline will be something like we will try to cover the the working or the a little brief mechanism of the working of BJTs, which are the bipolar junction transistors. Okay, so we will be discussing mostly about the physics aspect of it from the device part of it, which is the device physics. Then we will be talking about the common base and common emitter configurations most of the time. Then we will be talking about what are the limitations of the on the size of the emitter, the doping of the emitter, the doping, the size, and other things. Similarly for the base, for the collector, we will try to cover these aspects, and then we will move into the IV characteristics of these devices, of these configurations. Then we will study about something called as KIRK effect, and little bit brief about in the final slide we will talk about current crowding effect, which is the emitter crowding effect in the BJTs, and then we will briefly talk about maybe HBTs if the time permits. So this is the outline which also the professor has tried to cover in this particular session. So we will be mostly talking about it. So first of all, we will talk about what is BJT. So you know it's a bipolar junction transistor. It's a bipolar junction transistor, and bipolar means it has two polarities. Junction means you know that there are two depletion regions. So if we talk about let's say this is N plus, this is P, this is N. So there is a reason why I have marked this as N plus and this as N. So the emitter, this is called as emitter, this is called as base, this is called as collector, and this is from your basic fundamental courses. So this is actually a prerequisite of this course. Prerequisite that you should be knowing the basics of diode. You should be knowing the basics of maybe the diode means PN junction diode. You should be knowing the basics of BJTs, the MOSFETs. Those basics are actually the prerequisite that you should be knowing, but still I will try to briefly explain some of the things which you might not remember currently. So this is the actual structure of the emitter base collector, or the N plus PN region of the BJT. So you know the working is quite simple. So and in equilibrium, when you draw the band diagram in equilibrium, you have the band diagram which looks something like this. You all are aware about it. So this is the conduction band. So this is the valence band. This is the conduction band. This is the valence band. And the Fermi level is almost, let me draw it like this so that I can draw the Fermi level here. Fermi level is drawn here because this is P type, this is N plus type, and this is N type. Okay, I might not be drawing up to the scale, but this is how it looks like. So you see that there is a barrier in between, this particular barrier. The barrier is for the electrons because energy band diagram is drawn with respect to the electrons, so that your electron cannot directly go onto the other sides because of this barrier. Okay. Now what we do, we apply some voltage. We apply the voltage. Let's say we apply a negative voltage here. We apply a positive voltage here. If this is N plus, this is P, this is N. We ground this particular terminal because this is the base terminal. Then what is going to happen basically, as we apply the negative voltage on the emitter side, this part is going to go up, this part is going to go down, and you will have the split of the Fermi levels. That is quite clear from your basic fundamental device physics course. So this part will go up, and you will be having something like this. You will be having something like this. Okay, so band gap is not going to change. Band gap is going to remain same. So the drawing is not up to the scale. So this part is going up. This part is grounded, and this part is here. So these are the Fermi levels. So now if you have this, these are the Fermi levels. So this is Fermi level on emitter side, this is Fermi level of the base, this is Fermi level on the collector side. So now you know that the actual electron transfer takes place from higher Fermi level to lower Fermi level, and from this Fermi level to other Fermi level. So finally the electron will like to go at this particular Fermi level because this is the lowest Fermi level. Because in the layman sense, the Fermi level is the highest energy of an electron at 0 Kelvin, but this is just how we say it in terms of a layman. Otherwise the Fermi level definition is something different. But that's what how you can understand it. Now you have applied negative here, you have applied positive here. Electron will like to go into this direction, and it will fall, and you will have a current flow, which is basically the IC current. Now, what basically happens is that you know that this particular region, this is the base region, and it's p-type. This is N plus, and this is N. So p-type means it has excess holes. So the hole concentration is more than that of the electron concentration. So if this has more holes, so what is going to happen? These particular electrons, which are shown in red, they are going to there is going to be some recombination with the holes as well. That will be detrimental to the current flow. Okay, so there will be recombination. There will also be generation in this part. Let's talk about both of these. So that will be detrimental in this particular region because you want the current flow to be in this in the flow current flow to be in the forward direction only. So what is basically happening is that a small IB current, which is the base current, it actually triggers the base to emitter voltage. Okay, VBE. VBE is the voltage at this particular thing, at this particular end. Okay, so that basically triggers the VB, and the it increases the large current as exponential increase. So that is how the current basically increases. So you have a small base current that basically triggers the VBE, and it increases the collector current to appreciable value. That's why you write, if you have, let's say, electron going in this direction, you will be having emitter current flowing in this direction, the collector current flowing in this direction, and the base current flowing in this direction. So these are the terminals actually. So at this particular point, if you apply the KCL, you have incoming IC, you have outgoing this IE, you have outgoing IB. So IC will be equivalent to IE plus IB. That is, the collector current will be equivalent to emitter current plus base current. That is the fundamental equation you know. And if you know that IB is very small, of the order of microamps, so you can write IE to be IC to be approximately equivalent to IE. So that is the current which is basically flowing. And that is how the amplification of the current basically takes place, amplified, because of the very small current. So the limitation on this base region is it should be thin. So the base region should be thin. Why it should be thin? It should be thin because to avoid recombinations and other things. There are other effects also. It's also related to the base resistance. We will talk about it later. But obviously, if you want recombination to be less, you want the region to be smaller so that most of the electrons in the base region will go to the other region. So if the electrons are coming like this, most of the electrons should go to the collector region. So most of the electrons should end up here. This is collector, this is base, this is emitter. So this is the fundamental thing about the BJT you all know about. Now there are different configurations of these BJT. The configurations depend upon whether you make emitter as common, whether you make base as common, whether you make collector as common. This is called as common emitter, this is called as common base, this is called as common collector configurations. So we'll talk about these configurations, and we will talk about their current voltage characteristics as well. So now one of the important thing about this particular system with this particular BJT is, let's say we have a collector current, we have VBE, which is base to emitter voltage. So when you draw these particular plots, you see that the particular plots look something like this. This is not only collector current, this is also the base current we are drawing here. So this is basically the base current we draw, and this is basically the collector current we are drawing here. So this is the collector current, and we're drawing it with respect to the VBE. So VBE is increasing in this direction, maybe zero point 0.1, maybe 0.5, zero point 0.7 volts, so on and so forth. And what is basically happening is that we're drawing both the collector current and the base current on the same plot, basically. So now you see that there are different regions. There is this particular region, and there is this particular region, and then there is this particular lower region. At the lower region, both are almost similar, and that means there is negligible, let me write it, there is negligible collector current. And why it is so? Because this region is recombination dominated. This region is recombination dominated. So whatever is basically coming from the emitter is getting recombined in the base region. So you get negligible collector current. So for example, if 100 electrons are coming in, 90 electrons are getting recombined, and you get only 10 electrons. So that is a negligible flow of the current into the collector side. And this is basically the region where you want the current to be, where you want the collector current to be very higher compared to that of the base current. And this is basically something called as Gummel plot. Gummel plot. I don't care about the name, but the concept should be understood. But if you talk about now this particular region where you have the saturation, almost they reach to the saturation of they almost both attain the similar values. Okay, so there is something called as high injection which occurs at this particular region. High injection. So if you go on increasing the VBE to a very huge value, so high injection of these carriers takes place, and you have the variation in the Fermi levels, variation in the quasi-Fermi levels in such a way that the current no longer increases. Okay, so we are going to talk about this high injection effect and what effect does it have on the device characteristics. Now, if you talk about extrapolating, if you talk about this plot, if you draw the gain on the same plot now, let me draw the gain on the same plot by using the pink color. If you draw something called as HFE versus, let me not draw it here, let me draw it here. If you draw HFE, which is the gain, so let's not care about what HFE is. Basically, it's something related to H parameters. But let's say this is just a gain, which is, let's say, beta, which is IC over IB, the ratio of collector current to the base current. There are two types of these parameters. One is alpha, which is collector current to emitter current. The another is beta, which is collector current to the base current. Okay, they are used in different configurations, and we are right now talking about the beta. Okay, so it increases something like this, and then it drops with respect to collector current. Let's say this is an amps. So what is happening basically in this particular region? Again, I talked about there is high generation recombination currents being dominated, and in this region there is high injection effects being dominated. Okay, high injection effects. So that's why it's kind of saturating. The actual region where you want most of the things to work should be around in this region where you have at least a good beta and IC is greater, huge. So because you want the gain to be larger in these particular transistors. Okay, so now there are certain variations. There is, for example, the slope of this. Let's not draw it like this. The slope of this particular is negative. It's negative. The slope of this is something related to 1 minus 1 over m. What is this m? It's basically something called as ideal related to ideality factor. So ideality factor you might be knowing if you have a PN diode, then you write the diode equation as I naught e to the power qv kt minus 1. Basically, there is something called eta. This is the ideality factor. In this case, you assume the eta to be 1. But if you have some different value of eta, and what does this eta depend upon? It depends upon the recombination generations in this particular depletion region. Okay, so that is basically covered in the basic fundamental devices course. And if you write the HFE, basically the beta in these particular equations, you can write HFE to be approximately equivalent to IC over IB, which can be actually shown to be approximately equivalent to IC 1 minus 1 over M. So you can approximately write it in this particular form. With this HFE is something called as beta. So this is the current gain factor in this particular transistor. Now, what next? What we have next is, let me bring one more page. Now we have something called as common base mode and we have something called as common emitter mode of transistors. Okay, now what is basically going to happen? Let me draw a line here. Let me draw another line. So if we talk about the common base mode, then it looks something like this. If you have a transistor where the base is common, so this is base and this is grounded. So you have a base, you have an emitter, you have a collector, this is emitter, and you draw a symbol like this, and this is the base. So this is the collector current, this is the emitter current. So this side is the emitter, this side is the collector. So this thing is VBC. So this thing is VEB, all with respect to the base. So that's why VEB. And this is the base current, which is a very small current. And this thing is VEC. So these are the corresponding voltages of these common base mode. And now if we talk about the common emitter mode, so the emitter is common. So you can draw the configuration something like this, where this emitter is basically common, which is now grounded. So this is the emitter current. This is the collector current. This is the collector current. This is the emitter to collector voltage. This is again this is base, and this is emitter to base voltage. So this is something called as common emitter mode. So these are the certain configurations which are basically used, and what depend and we are going to see how it depends on whether we are going to use a common base or common emitter configuration, because what we are going to see is that the how we are going to see it, we are going to see it in terms of the breakdown voltage, in terms of the transconductance, in terms of the gain, in terms of the cutoff frequency. All of these parameters are basically going to depend whether you use a common base mode or whether you use a common emitter mode. So that is why these particular regimes or these particular modes of BJT are very important, because they directly affect these particular parameters. And if you are taking this course from the beginning, then you know how these parameters are really important for your high power applications and for your microwave frequency applications. Okay, so that is what we are going to see. So here we actually saw about how the conduction takes place, and what is the Gamal plot, and what is the how the gain of this particular BJT varies as a function of the collector current. It reaches the maximum, and then it starts to drop because of certain high injection effects. That's what we are going to look in the upcoming slides. What are those effects basically which saturated, which drop the gain of these particular transistors. Now, if we now look at the characteristics, now let me just take this particular picture. Whether I can take it? No, I cannot take it. But let me draw it. If we look at the current voltage characteristics in these particular FETs, not FETs. These are not FETs. These are not field effect transistors. These are BJTs. Okay, so if we look at the current voltage characteristics, we draw something like which is the collector current, okay, versus the VCB. Note that this particular B is here because it's with respect to the base. So we are talking about a common base mode. So it looks something like this. Let me draw it to the scale so that there is no ambiguity. Oh God. It looks something like this, where you are increasing the emitter current in this direction. Let's say this is zero point 0.1, this is zero point 0.2 milliamps, this is zero point 0.4 milliamps, so on and so forth. And this is the particular region, not like this. This particular should be aligned. Yeah, let me draw it like this. Okay, so this is with respect to the VCB, with respect to the collector to base voltage. Now, what is basically happening, and there is one more region which is basically here, and then there is cutoff. This is basically the region where the collector current drops to the collector current drops to zero, and beyond certain voltage, beyond certain collector to base voltage, this particular region, there will be breakdown. So this is the breakdown region. Break down region. So in this region, basically what it is showing is that you are not applying any emitter current. The emitter current is basically zero, but you are getting the collector current to be non-zero if you go on increasing the VCB to a very higher value. So that is what this particular breakdown region is showing. And now we are going to see that this particular breakdown region basically varies for common base and common emitter configuration. And how it varies, that's what we are going to see. Is basically can be justified in terms of the band diagram of these particular modes. But let's first of all talk more about now common emitter configuration. And one more important aspect of this common base configuration is that you have at let's say if your VCB is 0, you still have some current in it, and you have to apply a negative VCB in order to completely make the IC equals to 0. That means you have to apply a negative VCB in order to make the collector current to fall to 0, because you see that even if VCB is 0, you still have certain collector current at these particular points, these particular values. So that is fundamental to this common base mode. Okay, so that's what we are also going to see in one of the questions which will be asked, that why this thing happens in case of a common base mode. Okay, and it's related to how the current injection takes place in the common base configuration. Okay, irrespective of if we instead of see these current characteristics in common emitter configuration, we get something like this. We get something like this, where you have the collector current, let's say this is in milliamps, and we have the VCE here, which is with respect to the emitter, because it's with respect to the emitter. Okay, because it's a common emitter configuration, and you are applying, you are increasing the base current in this direction. So you see at this in this particular plot, this is basically the 0.0 volt. So yeah, at VCE equals to 0, the IC is equivalent to 0 milliamps in this particular configuration. And here it's not the case. The common base configuration at 0 VCB, you don't get a 0 collector current, which is usually which one should assume that at 0 voltage, 0 VCB, you should get a 0 current, but that's not going to happen in the common base mode. So that's what we are going to actually see. And in case of this the breakdown regions which we talked here, the breakdown voltage here, in case of the common, I should say common base mode, it is termed as VCBO. And in the here also you would be having some breakdown voltage beyond which there will be increase in the current. So this particular voltage will be VBCEO. If I'm using the notation correctly, I don't know, but it's mentioned in one of the questions. This is VCBO. This is VBCEO. Yeah, yeah, this is the breakdown voltage. Let's check the notations later on. So this is just the breakdown voltage beyond which the current starts to increase, even if you have not applied any of the input currents in any of the input small injection base current. This is basically a small injection base current. Okay. Okay, so now while the question is that why this thing happens, why you have a non-zero value of the current, even if you have if you have a 0 voltage applied at the collector to base terminal. So if you look at the base, if you look at the band diagram of it in a non-equilibrium scenario, when I say non-equilibrium, this is not the way to draw it. When I say non-equilibrium, I mean you have applied a if this is the if this is n plus p n region, that means you have applied negative here, you have applied positive here. As a result of negative, the band diagram on this side goes up, on this side goes down. So you have something like this. You have something like this. Okay, notes that this base region is very thin for the reasons I have basically discussed. So you have the Fermi level here, you have the Fermi level here, and you have the Fermi level for this here. So electron will like to go from higher Fermi level to lower Fermi level to lower Fermi to this Fermi level to this Fermi level. So that's how the conduction takes place. But now what is going to happen? We are going to basically see two different cases. The first case we will see, let's talk about, we vary VBE, which is the voltage around this end, and we keep the VCB as fixed. Let's keep this end as fixed VCB. So this is the first case we will talk about. Let me take it here so that I can compare these cases. So this is the first case we will be uh, talking about. Let's take it here. Let me take this here. And the second case we will be talking about will be if we keep the VBE as constant and if we vary the VCB. So these are two important cases. So these are all the voltage. The VCB is the voltage at this end. The VBE is the voltage at this particular end. Okay, so these are the cases which we will be talking about. This case and this particular case. So they are two different cases. So what is going to happen? First of all, let's talk about when we basically vary the VBE and keep the VCB as constant. So we are talking about this particular case. So if we look in the base region, basically, what is going to basically happen? This is the base region, this is the emitter, this is the collector. So base region is very thin, let's say 0 to W, which is the width of this base region. If we draw the minority carrier profile in this region, now let me just, for your understanding, let me magnify this region here so that you can clearly understand it. So this is basically W, which is the base width. So this is, let's say, this particular thing is its intrinsic carrier concentration, which is basically the doping concentration, which is the background doping concentration because it's p type. Okay, so it will be Pn0. And because there are certain electrons which are getting injected into the p region, because you have applied negative here, you have applied positive here. So because of that, there will be injected carriers, which is n in a p region. So there are electrons inside the p region. So that is going to look something like this. When you draw those minority carrier profile curves, so those curves are basically going to look something like this. They're going to look something like this. They are going to look something like this. So these are for different VBE voltages. If that means in this direction you are increasing the base to emitter voltage. Okay, that's what how it's going to happen. That means if you have very small base emitter voltage, your excess injected carriers will be something like this, which will be below the background doping concentration. As such, there will be negligible current flow. Okay, but that is the effect we are going to actually see in and we are also going to see in the other case also what's basically going to happen. Let's say let's say if I remove this color, so that is the case. You see that this particular this particular width here remains constant. This is the constant width of the base, constant width of base. Why? Because you are not varying the VCB voltage. If you vary this, as in this case, you will see that here, because you are varying VCB, you will see something called as base width modulation. Base width modulation. What does it mean? It means that W will start to change. You will have a change in the base width as well. But here you have a constant base width because you are keeping the other end of the voltage as constant. So now what is going to happen? So basically, if you go on increasing the VB, if you go on increasing the VB, you are injecting more and more electrons. So electron injection increases. And as you see from these curves, from the minority carrier profiles, we have the slope of the minority carrier profile at the emitter to base edge is this particular edge. So this is emitter, this is base, this is collector. So the slope of the minority carrier profile at this emitter to base edge determines the injected emitter current. So this is going to determine the injected emitter current. Okay, and you see that the slope is varying as you go on increasing the VB. The slope goes on increasing and increasing. So there are different slopes of the minority carrier profile in this particular plot, and this is particularly basically the injected. This is the injected current, injected electrons in this particular base region. Now if we look at the other case, if we have let's say this particular region where we again draw the minority carrier profile. So we have the background doping in the base. So this is basically the base region. This is the emitter region. This is the collector region. This is W, which is the width of this base region. Okay, let me draw it. Let me not draw it here. I will draw it later. So this is Pn0, which is the background doping concentration. And if you see again, what is going to basically happen? The curves look something like this. So they look something like this. You have the constant injected carriers, which is N on P side, which is the constant injected carriers which are coming from this region. They are at a constant value. Okay, why they are at constant value? Because you are maintaining this at constant. You are maintaining the VB at constant value. So that's why you are having a constant injected carriers. But now what is going to happen, because you are varying the VCB voltage? So because of that, there will be something called as early effect or base width modulation. So what does that mean? That means this width basically is going to shift. So the width, let's say earlier was this thing. it's going to now increase to this W dash, and it's going to increase to W, let's say double dash. And how it's going to increase? It's going to increase because you are increasing the collector current in this direction. Collector current means VCB you are going to increase. Okay, so that's why you're going to see shift in this particular point because of the increase in the base width. So this called as something called an early effect, and that means more VBC you are going to have a shorter and shorter base. More as you go on increasing the VBC, actually what happens is basically I have drawn it ulta. So if this is the base, if this is the actual base width, then this is the base width, then this is the another base width, and W is much greater than W dash is greater than W double dash. So you see the base starts to reduce. So it starts to become shorter and shorter as you go on increasing the base to collector voltage, or that's what I mean to say that IC starts to increase. So injected electrons is fixed, but you see that there is a that means this particular point is basically fixed, but you see that there is a change in the base width as a result of which the slope also starts to vary. So there are two effects. One is that if you keep varying the VBE, you have a change in the slope because of changing in the injected electrons. And the other case is if you have constant VBE, but if you are varying VCB, again you have the change in slope, but this time the change in slope is because of the base width modulation, because of the base width modulation. So these are two different effects which I want to separate because of the two different biasing regimes. Okay, so now what is basically going to what is basically the effect, and why we have a non-zero current in case of a common base configuration. So that was the earlier question we posed. Why non-zero IC at VCB equals to zero. So that was the question which we posed here at this in this particular plot, why there is a non-zero current in the common base configuration. So again, we can understand it from the band diagram directly and from these cases. Let's say we have a band diagram in non-equilibrium, which looks something like this, which I'm again drawing. This is a non-equilibrium case. Non-equilibrium means there are quasi-Fermi levels which are separated. So these are the quasi-Fermi levels. This is the base region, this is the emitter region, this is the collector region. So the electron is going to go from this end to this end, and it's going to go down the hill, and finally there will be the flow of the current. Okay, pardon me, this is collector. Okay, so that's how the this conduction takes place. Now, what happens basically? If you go on increasing the, let's say you go on increasing the VEB, that means the injected electrons go on increasing. That means starts to go on increasing. Let's say you have VEB equals to, let's say -1, -2, -3. You go on increasing this, you inject more and more electrons into this region. Okay. Now what's that going to create? Because you are keeping the base as common, so you're not changing anything of the base. Rather, you are only shifting these Fermi levels, this Fermi level and this Fermi level. You are moving it up and down because the base is grounded. So this particular region is static, almost. You are just modulating this particular region, these regions, and this particular region. Now, what is going to happen is that if you have, let's say for example, if you have some electrons coming in from the from the emitter end. Now because the biasing is applied in such a way, let me draw it here, maybe this curve shows it better. uh, Let me draw it on the other page. We are short of pages. Because the biasing is applied in such a way that this is negative and this is ground, this is negative, and this is basically you have applied positive because you have applied and this basically are connected to the ground, and this is basically the base is already connected to the ground. So your the profile looks something like this, which I have basically shown. Why am I not drawing it to scale? So this is emitter, base, collector, quasi-Fermi level, quasi-Fermi level, quasi-Fermi level here. So now what's going to happen? This the electrons basically which are coming into this region, even if you let's say are not applying any VCB. So that is the case we want to study. VCB equals to 0, but still IC is not equivalent to 0. Now that means you are removing the bias on this side totally. When you are removing the bias on this side, the Fermi level is going to be aligned with the base region. Okay, because you are not applying any bias. Earlier, this band diagram is for when you have negative here, when you have positive here, and this thing is grounded. But when you want to draw the band diagram for this case, how do you draw it? You draw it, let's say this is an equilibrium. This is an equilibrium. Everything is flat. Now you are applying, you are not applying any of the what we call VCB is basically zero. You are not applying any of the voltage, but there is some voltage at this particular end. So this side goes slightly up. So you have a region like this. You have a region like this where this is the quasi-Fermi level, and this quasi-Fermi level is flat. I'm not drawn it to scale. Let me try to the scale at least here. This quasi-Fermi level is flat. Okay, so what's going to happen? These electrons are going to spill over into the base region, and because of the high electric field here, where does that electric field come from? Because this is N region and this is P base, so you have the depletion region here. This is the depletion region. These are the immobile ions in the depletion region, and the electric field emanates from a positive charge and ends on a negative charge. So electric field direction is this direction, which is shown by this black arrow. So the force on the electron will be minus q times electric field. So force will be opposite. That means any electron which is basically here is going to feel the force, and it's going to come out on the collector side. Even if you are not applying any of the voltage here, if you have applied 0 volt here, VCB equals to 0. So, and this is particularly grounded. So that is why what happens is that there will be still some electrons which are going to the collector because of this huge electric field, because of the depletion region. So now what you do for it? How do you counteract? That means how do you make this particular regime? That means if you want the collector current to fall to 0, you have to apply some negative VCB on the collector end. That means on this side you have to apply a negative voltage also. What will negative voltage do? Negative voltage will shift this Fermi level up. So the Fermi levels will look like this. This will be emitter Fermi level, this will be base Fermi level, this will be collector Fermi level. Emitter, base, collector. So as a result, what is going to happen? If some electrons will come here, they will go dip here. Some electrons, let's say, will come here, they will go dip here, and there will be no conduction. That is what basically no conduction means. IC will be zero. There will be no flow of the conduction current, not conduction, the collector current. Okay, you are going to create the distribution of the Fermi levels in such a way that the overall current falls to zero. So that is what basically it means when we show in this particular plot that as you at some negative VCB, you have the collector current reduced to zero. Okay, so that's why the collector current is non-zero even if your VCB is zero because of this particular reason. So because of the electric field in the depletion region, there will be some certain electrons which can go to the other end. And you see that this region, this is the direction of the IE increase. That means VBE increase. Okay, are we writing it as VBE or VEB? Right, let's write it VEB because we are talking about common base. VEB. This is the VEB increase direction. So as you go on increasing the VEB at 0 VCE, you still have the current. Okay, and that is the reason, because if you are increasing here, increasing VEB means you are moving this region up and up. You are moving this Fermi level higher and higher. That means you are spilling more electrons into this side, more electrons into this side. And despite this and VCB at 0 volt, you still have the current flow. So that is what we want to negate. We want to omit this particular thing. So that's what we do on this particular collector side. We apply a negative bias, bring the Fermi level up here so that the Fermi levels are higher than that of the base. So whenever the electrons will spill, they will just go to the base, and in the base they will recombine. There will be no current flowing because the current flow is because the output current is the collector current. So the collector current will be zero, the emitter current will be zero, and there will be some base current that is of no use here, at least because all of the electrons are going to go into this region, base region, and they will get recombined there because there is the quasi-Fermi levels have split it in such a way. Okay, So that is the fundamental thing about this particular these particular plots. Now, if we talk about one more thing, which is basically the breakdown voltage, we notice that the breakdown voltage basically in case of a common base mode is greater than the breakdown voltage in case of a common emitter mode. So this is common emitter, this is common base. And why is that the case is because it is related to something, how we measure the breakdown voltage. Okay, if we talk about let's say a common base mode, how we measure the breakdown voltage is by making a floating emitter side. We float the emitter side. That means we completely omit it. We make IE equals to zero. Okay, because that is what basically in the curve it's shown. IE is zero. Then we start increasing the base to collector voltage. We start to increase this voltage. We start to increase, and we see that at what point the collector current shoots up. At what point this particular region arises. And we basically note that this breakdown voltage is higher in case of a common base configuration than in case of a common emitter. This is common emitter, this is common base. You can see the values here. Here it's 14. Approximately at 14 base to collector voltage, you have a breakdown. But in case of here, you have at approximately 8 volt, the breakdown is occurring. And that means occurring at earlier voltages. So the in terms of the breakdown, the common base mode is better than that of the common emitter configuration. Now again, why is that happening? That's what basically is related to how we measure this breakdown voltage. If we talk about this common base configuration, we float the emitter side, we make the IE equals to zero. So it leads to high breakdown than the common emitter configuration. Why? Because let's say you saw about the minority carrier profile, the minority carrier profile. This is zero, this is W, this is the base width, and here we are talking about this is the P0, which is the background doping concentration, and these are the injected concentrations, not this. These are the injected concentrations. This is N on P side. So this is the injected concentration, injected electrons. So we are talking about common base configuration here. So you see that as you go on, as you let's say this is the direction of the increase in the let's say this is the direction of the increase in the VBE. Let me write it as VEB. But the point here is what we do, we float the E side. That means we make the slope, we make the VBE approximately equivalent to zero. So when VEB is zero, you have negligible this particular curve, negligible injected carriers that is below the background doping concentration of the base region. So this is the curve. This is the curve when VEB is very small. So what is going to happen? It's almost having this particular curve is almost having slope approximately equivalent to zero. So as a result, there will be a low current flowing. Low current means low IE will be flowing, and this indicates that there will be low IC flowing in the overall system. So what does that mean? If you have a low IC flowing inside the system, you will have higher breakdown voltage. You will have higher breakdown voltage because the collector current flowing is very small. If you have a huge collector current flowing inside the system, then it will relate to earlier breakdown. Okay. Now, what is going to happen if we measure it for a common emitter configuration? For a common emitter configuration, we float the base. It's called as floating base. That means we make IB equals to zero. That is what basically shown in this plot. If you make IB equals to zero, then you start increasing the collector to emitter voltage. Okay, you start to increase the collector to emitter voltage, and you saw what is going to basically happen. If I draw it like this, if I draw the minority carrier profile, this is zero, this is W. Let me draw it like this. This is the background concentration. This is the NP injected carriers. This is the not like this. These are the minority carrier profile curves. They go on reducing as you go on increasing this is basically the direction of the let me draw it like this VBE increase, not like this. Let me drop this thing. Okay, So what is basically going to happen in case of the common emitter configuration, which is basically, where is the configuration? I draw it somewhere, which is this particular mode, in this particular mode. So what is basically going to happen? Because you are now floating this end, VEB, okay, you are not applying you're completely keeping it open. You are not applying any of the, you don't have any base voltage coming into picture. And what is that, how is that going to affect? That is going to affect that you are, and you are increasing this particular voltage, which is VCE. This VCE is going on increasing, VCE goes on increasing. So how, so what does that mean is that it causes the breakdown of this particular region, which is this particular region. Let me draw it in a new, if you have a, if you have the Fermi levels. So let's say this is VEB, this is floating, means this is open, this is VCB. Let me write it as let's write it as VCB for now. Then if you go on increasing this voltage more and more, you see that there will be a region, when there will be a regime when this particular side will break down, and as a result you will have a huge flow of the current. IC will start to increase. So that is basically how these conductions, or how these uh, breakdown occurs in these particular BJTs. So now what we are going to basically do is one more thing, is that we are going to look into something called as KIRK effect. So what is basically a KIRK effect? KIRK effect is basically related to high injection of the currents, high injection of the high. This is basically a high injection effect, and it means we have a very high collector current. That means we have a very high emitter current flowing inside the system, and it reduces the gain. That means it is detrimental for the performance. It reduces the performance of the transistor. Okay, so now what basically happens if you have a device like this? If you have this n plus region, you have p, you have n region, because there's a depletion region here. There's a depletion region here. So whatever the electrons present at this particular are coming from the emitter side into the base side, they are swept into the collector side. Okay, so they are swept into, because there's the electric field in this direction. So you have a very fast moving electrons. Okay, fast moving electrons plus immobile ions are here. Immobile ions are here. Okay, so when you solve the Poisson equation, in order to, let's say, when you draw the band diagram and other things, you need to solve something called as Poisson equation. Let me write the Poisson equation in 1D, which looks something like this. Okay, so this is the Poisson equation, where this is basically the mobile electrons. These are the mobile electrons. This is the immobile charges, which are the which are the immobile ions. So where does this come from? Is basically simply from this basically comes because the current is equivalent to NQ mu into electric field. This is basically the velocity. So current is basically NQ times velocity. So J is equivalent to, so you can write N equals to J over J over Q times velocity. So if velocity reaches the saturation velocity, which happens at these particular regions because of the huge electric field, so you have N equals to J over Q velocity saturation. Okay, and you already have a negative sign in front of this. Okay, now what is basically going to happen? So what basically happens, let me take this, let me write it here. So what is basically going to happen is that if you have, let's say, if you go on increasing the VB, you see that the emitter current increases, the collector current starts to increase. Okay, the collector current starts to increase. That means JC over Q VSAT is going to increase as a whole. But what is going to happen, because there's a negative sign in front of it? So this particular thing plus, let's say, some ND positive, this overall thing is going to reduce because there's a negative sign in front of it. So if this reduces, because this is proportional to dE over dx, so this is proportional to it, so the slope goes on reducing. Okay, slope of what? Slope of electric field. So if you draw the electric field profile, that will be a better thing to basically look out. So what is basically going to happen? You have the slope goes on reducing, and at a point you see that the base width starts to increase, and this is something called as base push out. As a result of which the current reduces, then the gain reduces, which is detrimental. The delays increase, and the transconductance reduces. So there are other effects which actually come into picture. Okay, so the current at which the Kirk effect comes into picture should be as high as possible, as high as possible. Now, how does this come into picture? We are going to picturize it in terms of the electric fields. Let's say we have the in terms of the if you want to look at the electric fields of the, let's say this is the emitter, base, collector. Let me draw the electric field profiles. Let me draw electric field profile for this junction only. The electric field profile will look something like this because there is a positive ion here, there's a negative ion here, so the electric field look like something like this. The charge densities will be like this. This will be positive, this will be negative. You basically find the electric field because it will be dou E over dou X will be rho over epsilon, which is basically what we wrote. It will be Q minus J over Q V sat plus N D plus. Okay, so that is basically the this there'll be epsilon also. There'll be epsilon. Okay. So now what you go on, what you see is that there, and this particular slope is basically slope is proportional to ND plus only. Here right now we have only ND plus. That's how you draw that's how you draw this particular electric field. So the slope is directly proportional to the ND plus. Now as you go on increasing the VEB, there will be free charges coming in. Now what is going to happen is that this slope is going to increase. The slope is going to increase. Rather, slope is going to reduce. dE by dx is going to reduce because free charges, which are the electrons, are going to increase. And because of the negative sign, the slope is going to reduce. So it's going to look like something like this. It's going to look like something like this. At a point, a slope becomes almost approximately equal to zero. So in this particular region, there is entire collector is depleted. So you have almost flat constant electric field. Constant electric field. Okay. Now you go on further. So in this direction, we are basically increasing the VEB value. That means injected current is basically goes on increasing. So at a moment, you see that what happens is that you have a total inversion in the direction of the electric field, or I should say, the slope of the electric field. It becomes negative. So there is a flip in the slope. Why it becomes negative? Because now the minus J over Q VSAT term dominates over plus ND plus term. So this becomes large. So you have a huge negative slope coming into picture. So dou E over dou X becomes negative. So you have a negative slope. Now you go on increasing it further. You see that this particular point shifts here and you have a electric field profile like this, which is having a negative slope. So you have at a point in here where there is zero field at base collector junction. What does it do? It spills holes to the collector. Okay, so this is something called as base push out. Base push out. So base just like pushes out the holes to the collector, and it is detrimental because it reduces the gain and it plays with the delays and other things. Okay, so that is why for these effects to mitigate these effects, we usually make the base thinner, which is better. But making the base thinner will basically include something called as base resistance. So there is always a trade-off when designing these particular things. Okay, so you see that when there is a point at which the field almost becomes equivalent to zero, the holes will start to spill over. So because you are increasing the VEB, so it will look like something like this. It will look like something like this. But this, let me draw it. Okay, so what happens is that there is a spillover of the holes into this region. Okay, this is called as base push out. So what is the threshold for Kirk effect? So threshold for Kirk effect is basically we can basically play with the doping of the collector region. Okay, if you want to mitigate the Kirk effect, basically Kirk effect, the which this thing which basically the collector current, which is Q times N D plus, let's say VSAT. Not, no, this is not exactly like this. So basically the this particular thing, the Kirk current should be as high as possible. So for that, we can go on increasing the doping. If we go on increasing the doping on the collector end, we can increase the J Kirk. Okay, but there is also a trade-off that it will reduce the breakdown voltage. So these factors are always looked into when we design. So this is something called as design optimization problem. Design optimization problems. Okay, so this is about it. Now there is one more thing which needs to be covered, but let me just take these things from here. Let me cut it. Let me bring a new page. Let me paste this thing here. There is one more thing which is basically called as base transit time. There is something called as base transit. Transit time is it's almost the same in almost all the aspects. It's the time which the electron takes to place to move in certain region. You have the PNP NPN transistor like this. So the time which the electron takes to move through this base region actually determines at what frequency is this device going to work. So it determines all of the performance of this device. And this transit time is basically approximately equivalent to the the charges divided by the collector current. And how this particular expression comes into picture, that is what we are going to basically see. So it's basically equivalent to the free charges divided by the collector current. So it's like not the free charge, it's basically the charge minority charge carrier divided by the current which is flushing out the charge, because electrons are flowing to this direction. That's how the collector current is flowing. So that is basically giving you the base transit time. Or you can basically write the base transit time to be approximately equivalent to QF over IC, which is basically equivalent to WB squared over 2 times the diffusion constant of the electrons, which is basically the diffusion constant of the electrons in the base region. Okay, so its unit is approximately centimeter square per second. So that's the diffusion constant of the electrons. And you might know that diffusion constant is approximately mobility times kT over Q, mobility of electrons. This is from the Einstein's relationship. And now, because the base emitter junction is forward biased, so you have a different capacitances. You have a forward bias capacitance, which is the diffusion capacitance. Because this particular junction, this is forward biased, so you have a diffusion capacitance. Once you have a diffusion capacitance, that is the diffusion capacitance is basically the change in the diffusion charge divided by the change in base to emitter voltage. Change in base to emitter voltage, which can be written as dIC into the transit time divided by dVBE. So you can write it is CD to be approximately GM times tau B. Okay, so now what is this? What is this basically? How does the GM come into picture? Because dou IC over dou VBE is basically GM. So let me write it as tau F only. Not confuse it. So this is basically, that means the diffusion capacitance is also related to the GM. So this will be the diffusion capacitance. So this diffusion capacitance can reduce the basically the cutoff frequency of a transistor, and it can be a killer, and it can be huge. Okay. So in base, what we want is that, let me take another page. So in the base region, what we want recombination current to be, let's say for example, we want recombination to be minimum. But if recombination dominates, what happens? If recombination dominates, then the recombination current in the base will be approximately equivalent to QF divided by base transit time. Okay, This is not actually base transit time. This is basically the base lifetime of electrons. Lifetime of electrons. Recall, I should say recall is related to the recombination time of the electrons. Recombination time of electrons. Okay. And you can basically from this you can write the beta is basically IC over IB, which is basically QF divided by tau F into tau B divided by QF. So you can write it is approximately equal to tau B divided by tau F. So this is the current gain factor. This is the gain factor, which comes out to be approximately equivalent to the base transit time divided by the recombination time of the electrons. So this is the minimum carrier lifetime divided by I should say this is the minimum, the minority carrier lifetime divided by the base transit time. So accordingly, you can see that if the base transit time increases, the beta reduces. You have a lesser gain. And on the other hand, if the minority carrier lifetime increases, the beta increases. That means you want the minority carrier lifetime to be greater. What does this mean? This means the lifetime of electrons more. That means they should recombine slowly. They should not recombine at all. Recombine slowly. Okay, this is basically related to the recombination time. If you have an electron, you have a hole. This is conduction band, this is valence band. So how fast does this recombination takes place? That is basically the recombination time, and that is basically what is the tau b, the minority carrier lifetime. How fast does this recombination take place? And it depends upon many factors. It depends upon whether the recombination is Shockley-Reed Hall recombination, whether it's Auger recombination. This takes place at high injection, high currents. Shockley-Reed Hall recombination assisted by the defects and other trap states. You have the Shockley-Reed recombination. So there are many recombination models which can be incorporated. So that's why modeling these particular phenomena is necessary in order to understand these amplification and gain characteristics of a transistor. Okay, this is about it. Now, what else did we cover in this week? We covered something called as okay, I splitted this. Going to the questions is a cakewalk after if you have understood this. Then we also cover something called as small signal model of a transistor of this BJT, which is something called as hybrid pi model. Hybrid pi model. Just give me a moment. I'll just have some water. Okay, so I had to basically open my fast. So let's talk about this hybrid pi model. So just to recapitulate what Professor covered. So we have something called as intrinsic model, which does not take into account any of the external parasitic resistances and capacitances. So if we have a common emitter configuration, this is the emitter, this is the base. You have a something called as C pi, which is the base to emitter capacitance. You have the resistance, let's call it R pi, and you have the C mu, which is the base to collector capacitance. You have a current flowing, and you have a output resistance. This is the collector. So this is the actual circuit model, and this current is basically Gm times VBE, which is basically the output current. Okay, and this output resistance is basically if you have a finite slope in the output characteristics. If your output characteristics look something like this, that means you don't have any slope. That means the output resistance is infinite. When this resistance will be infinite, it will be an open circuit here, and you won't be having any output resistance. But if there is a finite slope in this curve, like this, then you can basically extrapolate these lines, and they will join at a single point, which is something called as early voltage. Okay, because this is the voltage axis. And you can write output resistance basically to be equivalent to inverse of the slope of IC over VC. This is this, and it's equivalent to the early voltage divided by the collector current. So this is the output voltage. Now you talk about what is this R pi. This R pi is basically equivalent to, this is basically the input resistance, and it's equivalent to dou IB over dou VBE. It's basically its inverse, and it's approximately equivalent to KT over Q times IB, which is approximately beta times GM. And here the beta is basically IC over IB, so it times the GM. So you can write this R pi in terms of the beta and in terms of the other factors as well. And this C pi basically comes from the two sources, which is the junction capacitance, and it comes from the diffusion capacitance because if you have a forward biased base emitter junction capacitance is another, also one more source of capacitance. So that's why you see that when you draw the extrinsic model, in the extrinsic model you take into account the parasitic resistances and all. In the extrinsic model you see that these capacitances are not going to change, so that is also one of the questions. So in the extrinsic model, what you see that you have the same circuit diagram, but you have the base resistance, you have the C pi remains the same, but you have here one more resistance, which is basically R pi times 1 plus GM times RE. It's not one more resistance, there is this addition of this factor. Okay, and there is the C mu capacitance remains the same. Then you have the emitter resistance, and then you have another resistance here, which is the collector. The collector resistance basically comes into picture here. You have the collector, you have the output current flowing, and then you draw the circuit diagram of it. The goal of this course is not to make you understand the circuit, but just to give you a flavor of how these models look like. And these models are very important for something called as SPICE simulations. If you are doing the simulations, then you basically need to understand the current voltage characteristics. So in order to do that, you basically loop using the KVL and KCL equations. You write the KVL KCL equations and obtain the current voltage, the IC, the IB, the IE, and the voltage VCE, VBE, and all other voltage. So that can be obtained from by simulating in the SPICE simulator. Okay, so now what is the basically how is the GM, which is basically in this particular thing, the current will be GM times VBE divided by 1 plus GM times RE. So pardon me, this is actually a capital VBE. So there is a difference in what we when we so you have an important thing. When we write VCE, which is a capital, this is basically, it denotes the DC. When we write VBE, this basically represents the small signal, and that means the small with anything with the small subscripts are basically representing the small signal. So that's why the overall current will be the DC component of this plus the AC component, which is the small signal component. This will be the overall current. Okay, so that is will be the notation which is actually followed in all of the lectures. So if you have a DC, over it there is a small signal writing, which is basically IB. So this DC level is IC, so that the overall current is basically I. So that is basically the concept. And One more thing is that whatever the voltage will be applied here, let's say it's VC, it will, this is, let's say, applied voltage. It will not be reflected in the circuit. The reflected voltage will be VC dash, which will not be equivalent to VC. This is the true voltage, and this is the applied voltage. Why? Because there will be certain drop of the voltage around the parasitic capacitances, parasitic resistors and other which parasitic effects which come into picture. So that's why you might be knowing from your basics that you write VC dash to be equivalent to VC minus IC RC. You write VB dash to be equivalent to VB minus IB times RB. And you have the VE dash to be equivalent to VE minus IE RE. Okay, so these are the current voltage equations which can be looked into this hybrid pi model. So now what happens? What basically is important here? Now we are going to talk about one more thing, which is basically the cutoff frequency from this hybrid pi model. From this hybrid pi model. So what we see is that the cutoff frequency can be given by, it's a similar expression what you studied in field effect transistors. Okay, so this is equivalent to Gm divided by 2 pi, the capacitances, including the junction capacitance and the diffusion capacitance. So in the field effect transistor, you know that it was approximately equivalent to Gm divided by 2 pi C gate to drain capacitance plus gate to source capacitance. So it's almost like a similar expression. Okay, but not the similar thing, because the capacitances here mean a different thing. Now, there are a few things about the beta, which is basically the gain. If we talk about the gain, we write it as in decibel scale. People write it as something called H21, which is basically a H parameter. Let's write it as 20 log of H21. But let's say this is something called as gain, which is in a decibel scale. So this y-axis is in decibels, and this is, let's say, a log of frequency. So you see there will be a curve like this, and this particular slope is basically 20 dB per decade change. That means, let's say, if there is some value here, there is some value here, there is some value here, there is some value here. That means when there will be a 20 decibel drop here in the gain, the frequency will change by a decade. That means 10 times. So that means if a frequency here is 10, the frequency here will be 100. So that is what is meant by 20 dB per decade change in the frequency. So this is called as frequency roll off. Frequency roll off. And if you extrapolate this line, and it cuts the frequency line at this point where the gain drops to zero. So this is called as cutoff frequency. Okay. So it is the maximum frequency at which your gain drops to zero. It's the maximum frequency which you can give to a system, at which the basically in the log scale, in the decibel scale, gain drops to zero, which is 0 dB. The gain in decibels will be 0 dB. That means IC divided by IB will be equal to 1, basically. So that's what basically means the 0 decibels. There will be no gain. The gain is when the output is greater than that of the input. So if the output becomes equivalent to input, that is not the gain. Okay, this is the gain. So this is the gain. So this is not gain. So this is whatever you are giving at the input, you are getting at the output. If the output becomes less than that of the input, this is the loss. Okay, in that case, your the gain will become in the opposite direction. Okay, accordingly, that can be shown on a decibel scale. So what else we need to study? And these plots basically can be understood because they are like the poles of a transfer function. And the transfer function, you know that if you have a system, let's say a black box with some input which is x of t and output as y of t, then you can basically write the let me you can basically write this transfer function as Laplace transform of the output divided by Laplace transform of the input, and finding the poles of this particular thing, which is basically putting the denominator to equivalent to zero and seeing where the denominator or this transfer function will blow up. So that is going to give you the poles of this function, and that is basically actually related to the pole zero plot, and that's all related to these how you obtain these frequency characteristic plots. That's it's you might have studied as in a control theory or something like that. So why does this roll off take place? Now that is the question. Why roll off? The roll off takes place because that means the gain decreases as the frequency increases because the carriers cannot catch up. Carriers don't move faster with increasing frequency. Okay, because there is a finite speed of the carriers. Carriers cannot move as fast as you want because of finite speed of carriers. Okay, inside the here we are talking about the base region, or in the MOSFET we are talking about the channel. So eventually what happens that IC divided by IB becomes equivalent to 1, or IC becomes equivalent to IB. So you have the gain to be equivalent to, in the decibel scale, you have the gain to be equivalent to 0 dB. Okay, or the gain becomes equivalent to 1 in the linear scale. Okay, so eventually, and that happens at when F is equivalent to FT, which is the unity gain frequency. That is the fundamental concept of it. Okay, now what happens if we look at this FT unity gain frequency with increasing the collector current? We see that it should go on increasing, then it saturates. But what happens is that it kind of changes the, I should say, it goes on increasing and it shoots up, then it starts to reduce. And this reduction is because of high injection effects. Okay, it's basically a KIRK effect, which we talked about in the previous slide. So it's like something called as base push out. So the holes are getting injected into the collector. Okay, and near the collector base junction, the electric field approximately becomes zero. So it reduces this cutoff frequency. Okay, yeah, it reduces this particular frequency. Now, what are the considerations of the design for the emitter and the base? So now we are going to first of all move to the questions, then we are going to study these particular effects. So the first is the current gain versus the current gain beta versus the current gain which is basically here beta, which is basically IC divided by IB, versus the collector current is a, we have shown that if we talk about talk about the this plot. What was this plot called? I talked about this here, initial Gummel plot. We talked about the Gummel plot. Yeah. Okay. So we talked about the Gummel plot where we showed the IC and IB on the same plot. So this is like IB, this is like IC, this is IC, this is IB. And then you can basically draw the beta, which is basically IC over IB versus IC. You wrote this in terms of H parameter, some H parameter, let's say HFE. Okay, and you saw that it looks something like this. It goes on increasing, then it reduces. So it's like a U-shaped curve. And why does this happen? Because the recombination effects are dominant here. The high injection or KIRK effects are dominant at the higher collector currents. So these effects kind of make it to look something like this, which is a U-shaped curve. Okay, so you want to stay in this particular region so that you can have a good gain in this particular BJT. So this is a U-shaped curve. Now moving on to another, in common base configuration, when the collector to base voltage is zero, magnitude of collector current is not zero. That is what you saw. If you draw the collector voltage versus this is the common base configuration, so it will be VCB in volts. You saw what happens, that these particular points are not exactly at the, in fact, even if VCB is equivalent to 0, IC is not equivalent to 0. In this direction, you increase the IE. Okay, so what happens is that you have to apply some negative voltage, some negative VCB to make IC equals to 0. Okay, so that's the reason we basically talked about why this thing happens in case of a common base configuration. Okay, so this is the answer of this question. So if we talk about now the breakdown voltage, I discussed this breakdown voltage also, that for the common base configuration, which is the common base configuration, the breakdown voltage is greater than common emitter configuration. And this is also I discussed, and it can be also seen from this plot. The breakdown voltage for the common emitter is smaller than the breakdown voltage for the common base configuration. That means your common base configuration is going to sustain longer, large voltage, sustain large voltages before it breaks down. So it will be better for high voltage applications. Okay. So that is what basically this relation can be also looked into in this SMZ book, and we have discussed about this particular region. So the answer will be the breakdown voltage of the common base configuration is greater than that of the common emitter configuration, and it can be just simply understood by how you apply the voltages at these in these particular configurations. Just like in a common base configuration, you see that how this voltage is applied, and in the common emitter configuration, how this voltage is applied. So accordingly, if you have a smaller in the common base configuration, you have the smaller IC flowing, so you have higher breakdown voltage. Okay, higher breakdown voltage. And we are talking about a smaller IC when IE is equivalent to 0. That means VBE is equivalent to 0. That is when you talk about the breakdown. Okay, the breakdown is this region. If these are the curves and this is a 0, we're talking about common base. So we're drawing for this region. So this is the no current flowing, but suddenly the current shoots up here. So beyond this point is basically the breakdown voltage. Okay, and this is the point at which the emitter current here is 0, but as you go on increasing the VCB, you see that there is a shoot in the collector current. Okay, so that is basically the point we are talking about. All right. So which of the following components remain unchanged incorporating parasitic resistances in hybrid pi model? So we saw that the capacitances remain unchanged because these are related to the junction capacitances and the diffusion capacitances of the BJT. They occur in forward bias and reverse bias configurations. Okay, and they you know that these capacitances happen at to be occurring at these particular junctions because of the charge storage and other effects. And we saw that there's this particular model basically where this is C pi, then there is C mu. These capacitances do not change even if you include the other parasitic resistances like are the emitter resistance, the base resistance, the collector resistance. That's not going to change these internal capacitances at all because that they are related to the how the charge storage takes place. Okay. Now at higher frequencies, the typical gain roll off. That's what I also discussed. If you have a gain in dB versus the frequency, the gain roll-off falls as a function of frequency as 20 dB per decade. This is a number which basically comes. So you have a 20 dB fall for every 10 times change in frequency. That's what I talked. If this is 10, then this frequency is 100, then there is 10 times change in the frequency. And let's say this is maybe 20 dB. Then let's say for example this is 50 dB. Then this is 30 dB. So there is a 20 dB fall per decade change in the frequency. This is a decade change. That is the 20 dB per decade change in the frequency. And the cutoff frequency is defined where the gain is unity. This is the cutoff frequency again. If you extrapolate this point, this is the cutoff frequency ft, at which basically the gain is unity. Unity gain means that IC is equivalent to IB, but if you write this in terms of a decibel scale, that means it's 0 decibels. This is the 0 decibel. Okay, so that's also we discussed. With increasing collector current, the cutoff frequency, that's what I also showed. If you have a cutoff frequency and if you have a collector current, you go on increasing it, you expect it to remain constant, but it drops because of those high injection effects, which are the KIRK effects. And because of that, you have a whole spillover into collector region. And that reduces it. That means it increases initially, then it decreases. Why? Because of this particular reason we have discussed. So this Kirk effect is detrimental. So that's why you want the Kirk current, the current at which the Kirk effect comes into picture, it should be more. Okay. So that is the fundamental thing. The current crowding at emitter edge, this thing we have not discussed yet. The current crowding effect happens because if you have, let's say, you have a base, you have an emitter, you have a collector, then what is basically happening is that if you go on reducing the base, let me show it like this. If this is the base, this is base width. If you reduce the base width, the base resistance goes on increasing. Why? Because the base resistance is proportional to the length of the base region divided by width of the base region into the other dimension, thickness of the base region. Okay, so you go on reducing B, RB increases. Okay, so now what does this happen? That means the resistance of the base goes on increasing, and the current likes to flow through the I should say lowest resistance path. So this is the intrinsic device. So when this base resistance will go on increasing, the current would like to flow through the lowest resistance path. Okay. So what is going to happen? All of the current is going to crowd here. That's called as emitter crowding. And it's again a detrimental effect. Okay, so current crowds here. And for this reason, you want the base resistance to be low. But for that, you have to dope the base region. That means you have to increase the doping of the base region. And again, if you go on increasing the doping of the base region, you will have recombinations, you will have scatterings and other things of the electrons. So it is going to impact the output current. So output current is going to reduce. So because of these are something called as conflicting requirements, which I think the professor might have mentioned. Because of these conflicting requirements, you have switched to something called as HBTs, high heterojunction bipolar transistors, or 3,5 based these transistors, high frequency transistors. Okay, so that is the concept of this current crowding. So it reduces the base emitter voltage that the I should say intrinsic region sees. So that is basically the reduces the reduction of the base emitter voltage that the intrinsic device sees. Reduction in the base emitter voltage. Base emitter voltage is this thing. This is emitter. This is base. So this is base emitter voltage because of this effect. Okay, so ion implantation is preferred over diffusion. Why? Well, what does ion implantation do? It gives you a sharp doping profile. Sharp doping profile. So that is basically the exact reason. So you want the doping profile to be sharp in the emitter base collector region. So you want the doping profile to be as sharp as possible, just like this. If you have an N plus doping, you want this to be sharp. Okay, you want this to be as sharp as possible in case of these devices. That means this should particularly, and it should not diffuse into it. If you use something called as diffusion process, then the doping profile will look like something like this. It will diffuse because diffusion is mostly like a temperature dependent phenomena. But ion implantation is like you're bombarding the atoms, and depending upon the velocity you hit with it, you hit the material with those atoms are going to go deeper into this particular substrate, and accordingly they will dope it, and they will dope it sharply. So this transition should be as sharp as possible. And what is the other question? In a silicon drift transistor, the graded doping does not offer any significant advantage as. What is a silicon drift transistor? First of all, if we have, let's say, for example, what we do is that if we have, if we somehow in the base region, you saw that there is something called as transit time. So if you increase the transit time, or rather, I should say, reduce the transit time, the frequency is going to increase. How you reduce the transit time? By making the electrons go faster. And how you make the electrons to go faster? You either apply a field or you make a slope in the conduction bands. So that's what you do. You do the graded doping. You do the graded doping of the base region. So as a result, the conduction band profile looks something like this in the base. So there is a, if this is a Fermi level, this is a graded doping, means this is a highly p-type on this side. This is slightly lower p-type on this side. So because of this slope, the electrons would go down the slope and they will move very fast. So as a result, they will actually affect the transit time. They will reduce the transit time. So high electric field in the base. But because of it, there is a detrimental effect also. Because in this region, you see that there is a, what happens basically is that there is something called as band gap narrowing. the band gap narrowing. And this mostly occurs in case of a silicon, because in silicon you cannot change the band gap unless and until you don't apply a strain or band engineering or something like that. But so what happens is that because of the huge electric field, the there is basically a component which comes because of the band gap starts to reduce. So if this is, let's say, a silicon conduction band edge, this is the EK diagram, and the band gap looks something like this. It drops by delta E, let's say G. Let's say this is because silicon is indirect. Let me draw it like this. So this is delta EG. So band gap starts to narrow down at these particular locations because of the huge electric field. It's something like this. So you have a band gap narrowing effect at these particular positions. A particular thing will be to draw it like this. I'm exaggerating it here. Now, what is basically going to happen is that because the electric field is equivalent to kT over Q, 1 over the doping in the p-type, let me call it pp, dpp over dx minus 1 over q d delta eg x divided by dx. So what is this component? What is this basically? What this means is that if you have a, you know that, let's say you have a diffusion current, which is basically equivalent to q dp by dx, you know it, and you know also the electric field can be written in terms of the gradient of the field profiles, which is 1 over q dec over dx. Okay, let's not talk about it. Let's not confuse you here. But what I'm trying to see is that you have an additional effect because of the band gap narrowing coming into picture here, which reduces the overall effect. So what you thought is that the overall current is going to increase because of the slope, because you increase the slope, so you have the more drift of the current. Okay, but now what you saw, and you know that drift current is basically nq mu e, which is basically nq mu. Let me write it like this. Mu dou ec over dou x. There is minus 1 over q also. Q goes. So you can write it as n mu dou ec over dou x. So you have the drift current to be proportional to the slope of the conduction band profile, or as well as the valence band profile if we write for the holes. This is for the electrons. So accordingly, what happens is you expected this thing to increase, but what the band gap narrowing is doing is it is reducing the overall effect. So it's nullifying the effect. So the graded transistor, in case of a silicon, is not attractive. Okay, so it does not benefit at all. Why? Because there is a nullified effect of the electric field in the base because of the band gap narrowing. Okay, so because of this effect, the overall electric field reduces, and it nullifies the effect which was expected because of the graded doping. So that's why you use the other compounds, maybe 3,5 compounds or heterostructures, where you can actually use these effects for your better. You can use it, you can graded doping in order to increase these currents. You might have seen, if you remember, there was a concept of graded doping in one of the FETs. If I remember, that was the FET, where you do the graded doping, and you created a profile in the channel so that electron transit time reduces in the channel. Okay, this is a similar effect. Okay, so now that means the its effect is countered by the band gap narrowing at the base emitter junction. This is the base emitter junction we're talking about because of this huge electric field. Now I'm going to see whether this equation makes sense. The kT by Q, 1 over the concentration in P times dpp over dx. So this is just like a diffusion gradient looks like hmm, this is KT over Q. Okay, so if we write the diffusion currents, I'm going to see whether this makes sense. If we write the diffusion currents, we can write diffusion current to be QP dP over, let me write it as like this. If we write it for electrons, we can write it as NQ dN over dx, not NQ, it is Q dN by dx, but this is the diffusion constant, diffusion coefficient. And if you write for the holes, you can write it as Q, this is Q dP over dx. So we can write it as Q KT over Q mu n dN over dx plus Q KT over Q dP over dx. Why I'm writing this diffusion component, I just want to see whether equations make sense. This and this will go. We have KT mu n dN by dx plus KT mu p dP by dx. Okay, there is mu p here. And what we are writing here is this is J diff, diffusion current. You know from microscopic Ohm's law, you have the current to be equivalent to this is basically the drift. The drift current is sigma times the E electric field. This is the conductivity. And you can write conductivity as NQ mu times the electric field. That means you can write electric field as drift current divided by NQ mu. And drift current is written in terms of hmm, okay. So if let's say the drift current is equivalent to J diffusion, why are we applying voltage here? Drift current is equivalent to diffusion at equilibrium. Then this is actually drift. So you have electric field to be equivalent to J drift. Uh, Let me write it as J diffusion because equality in equilibrium and Q mu. You have for the electrons it will be KT mu n dN by dx over NQ mu. This goes. You have KT over Q 1 over n dN over dx. Similarly for holes you will be having KT over Q 1 over P dP over dx. Yeah, so this makes sense. So this is the electric field. And for the overall electric field, basically it reduces by this factor, and this comes because there's a change in the band gap. Now, okay, that is quite clear. Hmm. Okay, now it makes sense. These equations make sense. So these are, I was just trying to see whether these equations make sense or not. So that's right. We are done with the today's session. Is there any other question remaining? So what is basically we have tried to cover is some certain effects in the BJTs, and in the next lecture we are going to see let me check 3,5 and silicon germanium HBTs. So this is basically in this covered in this lecture. So we are going to cover HBTs and the 3,5 3,5 HBTs and silicon germanium devices for the high frequencies application. Particularly we are talking about microwave. So we'll be dealing that with in the week 10. And then we will be into week 11 and week 12. That will be the end of the course. And I hope you have enjoyed this particular session. So I'm going to end this particular session here. Sorry for the trouble because there's a problem with the Google Meet is not showing up a video currently. I don't know why this effect is happening, but let me try to see whether we can mitigate it in the next session as well. Okay, anyways, I hope you enjoyed the lecture. Thank you. See you soon in the next lecture. Bye bye.